Okay, so welcome everybody to today's One World Mathematical Physics seminar of the IAMP. It's a great pleasure to introduce today's speaker, Amanda Young from TU Munich, and the title of today's talk is A Bulk Gap in the Presence of Edge States for a Truncated Haldane Pseudopotential. So Amanda, we're very much looking forward for your talk.
All right, so thank you very much, first of all, to the organizers for the invitation. I'm very happy to be here today. And what I'm going to be discussing with you is kind of an ongoing work and project that I have going with Bruno Nachtigali and Simona Warzel. And I'll talk with you on results that kind of come from 4 different papers, although the bulk gap result is really the focus of the talk, and that is the latter 2 papers here, and that was joint work with Simona. So as the title says, we're going to be talking about a truncated Haldane pseudopotential. So I'll begin with talking a bit about Haldane pseudopotentials and their history and background. And then I'll move to talking about the main properties that these models are expected or known to exhibit. And in particular, Haldane pseudopotentials are Hamiltonian models for a 2-dimensional physical system. However, we're going to be working with the second quantized version of these models today, and in this transformation is going to turn into a 1-dimensional lattice model. So at the beginning of the talk, I'll give kind of a loose definition of what the Haldane pseudopotentials are. However, I'll give a much more rigorous definition once I introduce the second quantized version of the model, which will be a 1-dimensional model. And in particular, each Haldane pseudopotential is indexed by its filling. And the model I'll be focused on today is the 1/3 truncated pseudopotential. And in terms of the spectral gap conjectures, one of the reasons why this has been so difficult to prove for this sort of model is that while it's a short range model, it's not finite range. And in terms of the methods that exist for proving spectral gaps, they're much better suited to deal with models with finite range interactions. And this is the motivation, or one of the motivations, for why we are considering a truncated version of the model. So I'll also tell you what the exact truncated version of the Haldane pseudopotential is that we are considering. And when you're proving spectral gap results, what you typically try to do is look at a finite volume model and prove a uniform gap result that is independent of the system size. And as the title indicated, there are going to be some sort of edge states that kind of result or emerge in this model. And maybe this is a little bit misleading in terms of what you would expect to see from a fractional quantum Hall system, but I'll spend some time talking about what these edge states are and how you can actually recognize them in this particular system. These are going to be low-lying eigenstates that emerge in some particular parameter of the model. And then once I do that, I'll discuss with you what the main result is, which is the bulk gap that is somehow circumventing these low-lying edge states that appear for the model with open boundary conditions, but you don't expect to see for the model with periodic boundary conditions. Now, our strategy for how we proved this bulk gap, one of the main elements in our analysis was our ability to identify an abundance of invariant subspaces for this particular Hamiltonian in this particular system. And I'll spend some time going through what this general strategy is. And in particular, each of these invariant subspaces have a very nice description in terms of domino tilings of the 1-dimensional lattice that will indicate which orbitals in our lowest Landau level are and are not occupied. And each of these invariant subspaces will either support a ground state or an edge state, but not both. And that's one of the main key things that you need for applying this sort of strategy, is that you can segregate the ground states from the edge states. And then I'll briefly go over how we then approximated the gap. And the idea was, depending on the type of invariant subspace we were looking at, one that does or does not contain a ground state, we either applied a spectral gap estimating method that's been developed for quantum spin models, such as the Martingale method or Kanabe's finite size criterion. Or in subspaces that did not support a ground state, the gap is actually then going to be given by the minimal energy in that subspace. And so then we applied a technique that was meant more for estimating a ground state energy. And after I've gone through kind of this description, I'll turn and kind of pivot a little bit and talk about how we can use our bulk gap to also prove a property of incompressibility, which is one of these properties that you expect Haldane pseudopotentials to exhibit. And I'll also discuss a little bit, we have some conjectures on where we expect kind of the low-lying excited states, bulk excitations to live. And I'll describe a little bit how we can also use this sort of tiling picture to identify subspaces that we believe would support these eigenstates, and also some other mid and high range eigenstates that we can identify as well. All right, so Haldane pseudopotentials were first introduced as Hamiltonian models for the fractional quantum Hall effect. And so the physical system that you should keep in your mind is that you have charged degrees of freedom that are interacting on a two-dimensional manifold on which a perpendicular magnetic field is acting. And theoretical models for the fractional quantum Hall effect date back to Laughlin and his famous ansatz for the many-body ground state wave function. And it was very quickly shortly thereafter that Haldane actually introduced his family of Haldane pseudopotentials. He initially introduced them for odd integers p, and each integer p corresponds to a particular filling nu. This corresponds to the maximal filling of the ground state. And they were defined in terms of projections of a potential onto the lowest Landau level associated with the Fock space for the lowest Landau level associated with the particular geometry that you were investigating. And the value p here corresponds in particular to this potential. And these Hamiltonian models were catered or tailored, I should say, so that they had one of these Laughlin wave functions as a maximally filled ground state. Now, it was also realized later that for p even, that the Haldane pseudopotentials also were of interest. In particular, they could be used to model rapidly rotating Bose gases. And I particularly bring up this point because even though we're going to be talking about the p=1 model today, which corresponds to the 1/3 filling, all of the results that I'm going to discuss can actually be, or the spectral gap result, in particular the bulk gap result, can also be proved for the p=0 model and for a truncated version of the p=0 model. And in fact, the bulk gap for the p=0 model was our first result, and then we went back into the p=1 model. Now, one thing that has been conjectured for these Haldane pseudopotentials is that their main properties that they're expected to exhibit should be robust under a change of geometry. And so then a pragmatic way of trying to analyze these properties from my perspective is to choose your favorite two-dimensional geometry that may simplify the problem and try to first prove these models exhibit the conjectured properties there, and then see if you can transform this to other geometries. And so in particular, we have been focused in our work in looking at the cylindrical geometry. So we'll be considered with the Haldane pseudopotential in a cylindrical model. So on my next slide, I'll go through and I'll give the explicit second quantized version of the Haldane pseudopotential for the p=1 model on the cylinder or in the cylinder geometry. However, first, let me tell you a little bit about these main properties we expect to see in the model. So here we're going to let lambda represent our physical space. N is going to be the number of particles in our system. And then the filling factor will be just the ratio of n to the volume lambda. And so the first property that is known, that these pseudopotentials are known to exhibit, is that they have a maximal filling of the ground state. So here, if we have the zero energy states are going to be given our ground states for this model. And in particular, you can show that since this Hamiltonian is particle number preserving, that the eigenstates actually have a maximal filling, and that maximal filling is exactly what I had on the previous slide, is given by 1/p+2. And in particular, that the Laughlin wave function is actually a ground state of maximal filling. Now, you could also ask yourself what happens for higher fillings and what kind of energy states can you see there. So if you fix your volume lambda, you think about increasing the number of particles that you're putting into your volume. One thing you would expect to see in these models is that they have spectral rigidity, meaning that if you look at the lowest energy value in the in-particle subspace, that it is going to be proportional to some function that's an increasing function of the filling nu.
May I ask a question?
Sure.
So you set the entire Hilbert space of your theory as the Fock space?
Yes.
But how do you know that it is the Fock space? Because how, for example, what if some kind of wave function renormalization is needed? Can you exclude that kind of possibility?
So we're taking the Fock space generated by the lowest Landau level. And from there, it's because we're looking at second quantization. So in that sense, I think it's quite natural. I'm not exactly sure what the concern is.
Yes, for example, the 5-4 theory in 3 dimensions needs infinite wave function renormalization. So the underlying physical Hilbert space is not unitarily equivalent to the Fock space. So
Mincho, so this is a condensed matter problem. So this is a non-relativistic condensed matter setting. So there's nothing like renormalization, ultraviolet divergence.
Oh, I see. Okay.
All right. Yeah. Thank you, Hal. All right. So and yes, and please interrupt with questions. I'm not always so good at checking the chat, or if there is something in the chat, please feel free to point it out to me. Okay, great. All right. So yeah, as I was saying,
but Amanda, I have a question. So is this the physical space lambda a continuous space, or it's a lattice?
Right. So I'm being a bit loose here. In the second quantized region, we're going to have a one-dimensional lattice model, and so I'm going to have a finite volume lambda, and so then it's well defined as in terms of like the number of sites, which is going to correspond to the number of Landau levels that we have in our system, because they're kind of localized in space. Yeah. Good question. All right, so we have here the minimal energy should be an increasing function of the filling. And so if you think of lambda as being fixed and n is increasing, you'll see that the minimal energy in the n particle sector is going to be increasing. And this is going to be, for those of you who are familiar with the rapidly rotating Bose gases, this is related to what's called the Urs line. So the main topic of today's talk is the spectral gap conjecture. And in particular, this is the spectral gap above the ground state energy. And we expect that the gap of the Hamiltonian for a finite volume lambda is going to have can be uniformly bounded from below by a constant that's independent of the system size. And I also want to emphasize that we're not fixing particle number here. So this is also independent of the particle number. So I'm looking at the ground state as being all of the zero energy states. And I'm looking at the next highest energy amongst any possible filling. And I'm looking at the gap between those two values. And so that gap can be uniformly bounded from below by a constant independent of the system size. And one consequence of the spectral gap will actually be the incompressibility. And a kind of a naive way of seeing this is that there's two ways to change the filling. One is to increase or decrease the number of particles, but the other would be to change the actual volume of your system, to try to compress it. And so if you fix the number of particles, but then try to compress the physical system, the physical area, lambda, what the spectral gap conjecture, or what the spectral gap would tell you, is that there's a finite amount that you can actually compress the system before you'd have to jump in energy, because you couldn't be in a ground state after a certain filling, as the ground states have a maximal filling. And then the final property that you expect to see is anionic excitation. So, you know what the ground state is. What about the low-lying excitations above the ground state, the bulk excitations? We expect those to have fractional charge. And these are the main properties that we expect to see exhibited in these Haldane pseudopotentials. Some of them are known, some of them are not known. But what we did was we wanted to see if we could recapture these properties in a truncated version of the model. And we were able to positively answer yes for the first three properties and show that the first three properties do hold for the truncated version that I'll present on the next slide. And we have some partial results and some conjectures for the fourth point. However, more work would definitely need to be done to make this more concrete. All right, so as I said before, we're going to be looking at the Haldane pseudopotential in the cylindrical geometry. And we're going to be looking at the second quantized formulation. And so here, we're going to look at the nu equals 1/3 filling. So we're going to be looking at the fermionic Fock space generated by the lowest Landau level. And the lowest Landau level is going to be spanned by wave functions that have a natural index by a parameter k. And that parameter k will actually have a spatial meaning as well. And it'll correspond to where along the x-axis the wave packet is localized. All right, so in this sense, the wave functions naturally index kind of spatially where the particles are localized. And so when we actually look at the second quantized version of the Haldane pseudopotential, which is written for you here, the creation and annihilation operators preserve the spatial locality in the system. All right, so this is the Haldane pseudopotential for p equals 1. If you were to choose a different value of p, the thing that would change would be the rapidly decaying function here in the definition of this operator b sub s. And what this potential is really a sum over of non-negative terms that are corresponding to a center of mass. So you should think of this half integer s as being as a center of mass. So it's telling you for particles that are hopping how far that they have to say equidistance from the center of mass s. All right, and so this operator though b of s is very short range in the sense that if you look at the annihilation operators and you look at the two-body function that you get from particles that are k steps away from the center of mass, that the coefficient in front of it is rapidly decaying. So this suggests that if you were to truncate these operators b sub s just to the first few leading order terms, that it should still possibly well capture the physics of the system, and that if you wanted to try to then look at the full Haldane pseudopotential, you might be able to treat the remaining terms as if it were a perturbation. So this is the approach we took. And the particular truncated model that we considered was first introduced by Sabine Janssen in a work from 2011. And also shortly thereafter, these two works actually appeared only 2 months apart on the archive by Nakamura, Wang, and Bergheltz in 2012. And it corresponds to truncating this term b of s to the values of k that are at most 3/2. And depending on if the value s is integer or half integer, this produces two types of interaction terms. So for centers of mass s that are integer, it produces a truncated term that will give you an electrostatic term. And for half integer terms, it'll produce an interaction term that'll correspond to a dipole hopping term. So for the electrostatic term, it's going to penalize having particles being next nearest neighbors. We'll have an energy penalty there. And then for the dipole hopping term, it'll take particles that are nearest neighbor, hop them to being 3 sites apart and back and forth. Now, this is the truncated interaction that we take. But when it comes to proving spectral gap estimates, I mentioned at the very, very beginning that one strategy to do this is to take finite volume models or finite volume Hamiltonians and produce a lower bound on the spectral gap that's independent of the system size. So here, what that's going to correspond to is taking a truncated cylinder, which will correspond to, for us, taking a finite, the Fock space generated by the orbitals corresponding to a finite subset of the lowest Landau level. So to be a bit more concrete, here is the actual finite volume truncated model that we take. Instead of keeping the parameters, the physical parameters that I had on the previous slide, I'll instead renormalize them and just use two parameters, kappa and lambda. So lambda will be allowed to be any complex number and kappa will be taken to be positive. And then for any finite interval of the integer lattice, the finite volume Hamiltonian with open boundary conditions will have the following form. You'll have your electrostatic term that's going to penalize having next nearest neighbors. And then you're also going to have the dipole hopping term that's going to take next nearest neighbors to 3 sites apart and back and forth. So that's what's illustrated in this picture, the action of the Q star Q. And then the Fock space will work really with the quantum spin model more or less. But the Fock space has a nice representation in terms of its occupation states, where here the orthonormal basis will be labeled by Ketz of either zeros and ones, and it'll correspond to which orbitals from the lowest lambda level associated with this interval are and are not occupied. Now this model has two symmetries. As with the original Hamiltonian, it's particle number preserving, and it also preserves the center of mass. Now, if we go back to the original model that I had on the previous page, notice here that we had this coefficient here was in terms of a parameter alpha, which is the ratio of the magnetic length to the radius of the cylinder. And in particular, where we're going to see these edge modes appearing is in a particular limit of the parameters, and it's going to correspond to the limit from the physical regime when we take the radius in the tau thales limit. So that's taking the radius r to 0. And in this situation, the parameter lambda is going to tend to 0, and the parameter kappa is going to be robustly order 1. Excuse me. All right, and then so just to reiterate that the main point here is that we want to prove a uniform ground state gap. So we're going to look at the spectral gap of the Hamiltonian above its ground state energy. You can show that this Hamiltonian is non-negative and has a non-trivial kernel, so its ground state energy is going to be 0. So what we're really trying to estimate then is the first excited state of the Hamiltonian. And we want to prove that this first excited state can be uniformly bounded from below by a constant that's independent of the size of lambda. Now, of course, the value of the gap can also depend on the model parameters, kappa and lambda. And in the original work that I did with Simona and Bruno in 2021, what we were able to show was there was a constant dependent on kappa and lambda that was robustly order 1, so that if you take any non-zero value of lambda that has modulus between 0 and some constant, this constant is dependent on a function, so 5.3 is not strict, but it gives you a good idea of the regime that it does apply to. And as long as you looked at intervals of lambda that were length at least 11, you could bound the gap of any Hamiltonian of length L from below by this order 1 constant times the minimal gap that you would get for a Hamiltonian on an interval of size 7, 8, or 9. Now, this is great. This is typically the kind of thing that you want to show for a uniform gap result. However, what we found is that the spectral gap of these 3 finite volume Hamiltonians was proportional to the modulus of lambda squared. So as lambda tends to 0, this gap looks like it's closing. But when you looked at the numerics for the model with open boundary conditions, or even if you just took lambda equal to 0, which becomes a Hamiltonian with a commuting interaction, so you can compute the gap explicitly, what you found is that the gap for lambda equal to 0 was the minimum of kappa and lambda. So it was actually a gap system. And what you saw for the numerical side of things is that you have these low-lying edge states that for positive lambda are tending to 0 and closing the gap. However, if you also then looked at the numerics for a system of, say, size 9 sites, and you look with instead the model with periodic boundary conditions, you didn't have this behavior. You would see that you have a robust order 1 gap in the limit lambda going to 0. So this is what alerted us to the fact that there are potentially edge states in the system that, for the model with open boundary conditions, aren't giving us a good approximation for what the true gap is in the thermodynamic limit. And in fact, we were able to find such edge states, and an example of such edge states is given here. So we were able to show that if you take the occupation states that are spanned by 2 kets, where each state has exactly 3 particles, here we have them to the left side of the system. And so it doesn't matter what the size of lambda is, you have this 2-dimensional subspace spanned by 2 occupation states of this form, where you have 0 states here. That indeed that this 2-dimensional subspace has a ground state, or excuse me, it has a low-lying edge state of order of absolute value of lambda squared. So this approximation that we got here was actually quite tight. However, though, if you think about what happens when you take the thermodynamic limit, so you're thinking about letting both ends of your open interval tend to the infinite volume limit. These particles would tend off to infinity, and what would be left is the vacuum state. And the vacuum state is actually a ground state of the Hamiltonian. So you would expect that perhaps this low-lying edge state doesn't persist in the thermodynamic limit, and that the gap of the bulk gap would actually be robustly order 1. So what this indicates is that actually what you should look at, instead of the model with open boundary conditions, you should try to prove a uniform gap estimate for the model with periodic boundary conditions. So in the same work with Bruno and Simona, we tried to do the same thing, but in the end, what we got is, again, an estimate that was order of lambda squared. Now, the reason for this estimate, though, was not because of the fact the model doesn't truly have a bulk gap, but rather it was a artifact of the existing gap methods out there for proving spectral gaps for models with periodic boundary conditions. The main approach when you are looking for a spectral gap for a model with periodic boundary conditions, the main idea is that if you have an interaction that is sufficiently local, then you expect low-lying excitations to only occur in a finite region of space. So they should be a local excitation in the physical system. And the idea behind many spectral gap methods for getting uniform gaps, the idea is to use the gap of a finite volume Hamiltonian that kind of traps the excitation, and use the gap of that Hamiltonian to approximate the gap for the larger system. And then if lambda prime can be chosen, the subregion can be chosen independent of lambda, that's how you get the uniform estimate for the spectral gap. Now, for periodic systems, you can kind of already see what the problem is going to be. When you take this sub-Hamiltonian, you're going to be looking at a finite region of a model with periodic boundary conditions, but the natural Hamiltonian that will arise from that is a model with open boundary conditions. And so if the model with open boundary conditions suffers from these edge states, the lower bound estimate that you're going to get for the model with periodic boundary conditions is going to reflect the estimates that you get from the edge states. And so the main difficulty in trying to prove a bulk gap is trying to circumvent this need for using the edge states of the model with open boundary conditions to approximate the gap of the Hamiltonian with periodic boundary conditions, which you suspect does not actually have these low-lying edge states. And so it's particularly or precisely this problem that we were able to circumvent with our strategy. And then this is our main result. So we were able to show that for all values of the parameter lambda in the Hamiltonian that are non-zero, such that when you plug them into a function, the absolute modulus of lambda squared, and it's less than 1/3. In particular, this is where this number 5.3 came from. You can get a uniform lower bound on the spectral gap for the model with periodic boundary conditions that is robustly order 1 in the parameter of lambda. So it's bounded from below by a minimum of 4 constants, or 2 constants. The one is this gamma pair, and the other is this constant that's given in terms of this function f. Now we have a closed form description for f, but it would require me to define quite a few things, and it's not very elusive, so I prefer to just give you the graph. But what you can see is that as lambda goes to 0, that f of lambda also goes to 0, and so this would give you something that's robustly order 1 in the parameter of lambda squared. And then this gamma pair is also robustly order 1 in the as lambda goes to 0 as well. So the main take home here is that the spectral gap remains open despite the fact that you have these edge states for the model with open boundary conditions. And again, just to reiterate, you can also get an analogous result for the 1/2 filled model, which is a bosonic model and corresponds to the p = 0 model, or pseudopotential. Okay, so here's the idea behind our strategy. It's actually rather simple, which I quite like. So the idea is to block diagonalize our Hamiltonian in such a way that we segregate the ground states and the edge states. And if we can block diagonalize our Hamiltonian in such a way that the ground states are in one invariant subspace, then when we're trying to approximate the gap of the whole Hamiltonian, the way you would do it is 2 different ways. So number 1, in the first invariant subspace, you're trying to look for the first excited energy in that subspace, or the second lowest eigenvalue in that subspace. That's going to approximate, you just need that to approximate the gap or in that subspace. However, in the orthogonal complement, you know that you have no ground states. And so in this orthogonal complement space, what you're really trying to do is approximate the minimal energy. Now, if you're looking at the Hamiltonian with periodic boundary conditions, even though the edge states for the model with open boundary conditions lie in this other invariant subspace, when you're trying to approximate the ground state energy of a Hamiltonian, the methods that you actually apply are quite different than when you're trying to approximate a gap. So this issue that I mentioned before of the fact that the methods exist require you to localize an excitation and then use the gap of that Hamiltonian to approximate the gap of the other Hamiltonian that you're interested in, no longer applies. And instead, we're going to be able to use ground state approximating methods to estimate the minimal energy in this subspace. And we'll be able to ignore the low-lying edge states that you get for models with open boundary conditions. Those energies will not appear in the actual estimates that we obtain. And it's exactly this segregation that allows us to get a order 1 bound on the bulk gap. Now, the other main property that you're going to need to make sure that this strategy works correctly is you're going to need an isospectral relation, which more or less shows that when you look at this first subspace that contains the ground states for the model with periodic boundary conditions, that it respects the subspace you would have obtained for the model with open boundary conditions, because we're still going to want to apply spectral gap methods for quantum spin models in this particular invariant subspace. So for the finite volume systems that we see here, we should also obtain more or less the same subspace that we would have gotten here for the model with open boundary conditions. So we're going to need this isospectral relationship that's going to allow us to make sure that the gap estimates we get for models with open boundary conditions actually do lift to the periodic system in the right subspace. All right, so the main question at this particular point is how do we construct these invariant subspaces? We want to make sure that we construct an invariant subspace that supports all of the ground states of our Hamiltonian. So now it becomes a question of what are the ground states for this Hamiltonian? Now this interaction is non-negative. The interaction terms are all non-negative. And so in particular, and it actually has a non-trivial kernel. So what this means is the Hamiltonian is what's called frustration-free. And so to find the kernel of the Hamiltonian with either boundary conditions, open or periodic, what you're looking for are vectors that are simultaneous eigenstate or simultaneous ground states of every individual interaction term. And so we can start to try to build what these ground states look at from the configuration states that we have that generate the whole Hilbert space. Now, the electrostatic term penalizes having two particles occupy next nearest neighbor sites. So in fact, you can show, or it's very easy to see that the configuration states are a orthonormal basis of eigenstates for the electrostatic terms. And the configuration states are ground states if and only if the filling at next neighbor between any two pair or any pair of next nearest neighbor sites is at most one. Now for the dipole hopping terms, these interactions act non-trivially only on an interval of 4 sites. And on an interval of 4 sites, you can show that this operator Q, that the eigenstate, or excuse me, that the kernel of this operator Q has at most 2 particles on any interval. So if you have 0 particles, it's a ground state, 1 particle, it's a ground state. And you only really have to look for non-trivial ground states in the sector with 2 particles on this interval of length 4. And in particular, if you have the 2 particles bound to the left or to the right of the interval, it's going to be a ground state. And the only non-trivial ground state you get comes from a linear combination of the 2 remaining states with 2 particles. In particular, the ones that you know already would satisfy the electrostatic condition. And it's given by this state here, which says that to hop particles that are on the boundaries of your interval of length 4 to being next nearest neighbor, you would cost it would come at a cost of the parameter lambda. And so what this suggests is that you can build a ground state starting from configurations that come from repeating the pattern 1 0 0 1 0 0 1 0 0. And so we're going to introduce what we call a monomer tile, which is precisely this tile that has a particle on the first site and no particles on the next 2 sites. And what this dipole hopping term suggests is that to build a ground state, we need to have a replacement rule that says that any 2 neighboring monomers can be replaced with what I'm going to call a dimer tile, which has length 6 and it holds 2 particles. And that if you look at all of the configurations you can construct using this replacement rule, that neighboring monomers can be replaced with a dimer. This will generate overall a finite set of configuration states that you can use to generate an invariant subspace of the Hamiltonian. And moreover, that this invariant subspace is going to support a ground state. And that ground state is going to be given by the sum over all of these different tiling states, these different configuration states you've generated with the tiling. And then the coefficient in front will correspond to the number of tiles that you replaced with the dimer. And so that the number of factors of lambda you get here will be the number of dimers in the tiling. So for this bottom tiling, you would have 2 dimers, so it would have a coefficient of lambda squared. And this ground state in particular was studied in depth in Sippin and Janssen's work, and I think it also has origins to a previous work of Hor's as well. And this really motivated how we then proceeded to try to construct other invariant subspaces with ground states. And the idea here is that it's going to follow a similar pattern, but one way you can see that other ground states can be constructed is that in this, what I'm going to call the root tiling here, where we just use the monomers, I could have also inserted extra zeros between the two monomers, and I would have still been able to construct a ground state. By inserting these extra zeros, all I've done is separated the particles enough that the hopping term could no longer cause the two particles to jump back and forth together. You've separated them and more or less created a domain wall. So this motivated our definition for a more generalized tiling picture. And these root tilings that will generate the full invariant subspace can be tiled using a finite subset of tiles. So here we have the monomer from the previous slide. We have what I call a void, which corresponds to putting zeros throughout the volume. And then the other thing that can happen is that you can get truncated versions of these tiles at the boundary. So here we had two different types of tiles that we really introduced. We had the monomers, but we also had the dimers. And if you thought about tiling the entire integer lattice using these monomers and dimers, the types of finite volume tilings you should get come from truncating those tilings at any point to create your finite volume system. So these other boundary tiles come from truncations that would come if you were to cut, say, in the middle of a tile. So we get these boundary, void, monomer, dimer tiling spaces. And for the root tilings, you can put the voids and monomers anywhere, but the boundary tiles can only go on their respective boundaries. So if you use them, they can only go on the correct boundary. So there's one tile that you need for the left and 3 tiles for the right to uniquely define all of the configurations. And then once you have, excuse me, a root tiling, you once again introduce a replacement rule where you can replace 2 neighboring monomers with a dimer tile. And for the right boundary, since we have 2 tiles that correspond to monomers, we also have to introduce truncated dimers that we can put at the right boundary as well. Again, the collection of configuration states that correspond to all of the different tilings you can get from applying the replacement rule to the root tiling will produce an invariant subspace of your Hamiltonian, and it will support a ground state. And it will support a ground state using the same rule that we had before. You sum over all of the tilings that are obtained from the root R, and then you multiply it by the value lambda to the number of dimers in the tiling. Now, a similar picture also works for the Hamiltonian with periodic boundary conditions. The number of tiles you need is much simpler though, because you no longer need the boundary tiles. So for the model with periodic boundary conditions, you just tile, you make all of the possible root tilings with the voids and the monomers, and then you have the generic replacement rule that neighboring monomers can be replaced with a dimer. This will similarly construct invariant subspaces that support a unique ground state. And moreover, this will support all of the ground states. And the same is also true for the model with open boundary conditions. I forgot to say this, but this will produce an orthonormal basis or an orthogonal basis for the ground state space. And in particular, one thing you can see is that for the model with periodic boundary conditions, the tiling spaces that we've generated by taking the direct sum over all of the tiling spaces generated by these various roots you can have is contained in the tiling space with open boundary conditions. And some key properties to point out is that number one, this ground state space is quite extensive. And this is one of the other reasons why proving spectral gaps can be quite difficult. So we have the dimension of the ground state space grows exponentially in the system size. And you can also see from this tiling picture that indeed you do have the maximal filling property for this truncated model, that the number of particles, the maximal number of particles that you can support on a ground state is exactly 1/3 of the volume size. And that can be seen from the fact that the maximal tiling would correspond to using just monomers in your tile, which corresponds to filling of 1/3. All right, so as I mentioned before, one of the other key relationships we need for this spectral gap strategy is the fact that the tiling spaces for open boundary conditions and for periodic boundary conditions have a nice isospectral relationship. And that can easily be seen from the open for the tilings from the periodic boundary conditions, because remember, the idea is to try to trap an excitation to a finite region of space and then use the spectral gap of the Hamiltonian for that finite region of space to approximate the gap for the larger system. Now, when you restrict to the tiling space, the Hamiltonian for a finite region of space will only see the occupation of the tiles for that region. So this exactly corresponds to cutting the various tiles possibly in the middle of the tile. But as I said before, this is kind of what motivated our definition of these boundary tiles. And so if you were to cut a periodic tiling into a finite region, it would produce a tiling for a model with open boundary conditions that corresponds to a root for the Hamiltonian with open boundary conditions. So a particular consequence of this is that if we were to look at the Hamiltonian associated with open boundary conditions on the subregion and restrict its action to the tiling space, say, associated with the model with periodic boundary conditions, the spectrum of this Hamiltonian restricted to this tile subspace is equal to the spectrum of the Hamiltonian when you restrict to the tiling subspace with open boundary conditions associated with this interval. And this is the key relationship you need to be able to get the uniform gap result for the tiling subspace. Now, I've talked with you a lot about the ground states, but what about the edge states? Where do the edge states live? So unlike the ground states, we don't have a nice closed form for the actual wave function itself, but we can identify invariant subspaces of the Hamiltonian that do support the edge states. Excuse me. And these are generated by, these invariant subspaces are again generated by a root tiling. However, instead of just using the tilings that I introduced for the ground state space, these invariant subspaces will have to have a boundary tile on at least one of the two boundaries, left or right, and it must contain one of these two boundary tiles. And how you obtain these tiles is by taking either the left dimer tile or the right dimer tile, cutting off the interior zero, the last zero, and then appending the monomer to this truncated tile. And what this does is it puts the particles just close enough together so that they can then interact with the dipole hopping. However, if you were to look at the tiling space that it generates, and you will have to introduce some new tile replacement rules, but let me maybe not talk about that too much. But the main thing is that if you were to cut off this leftmost particle, the configuration you would have left over would be a tiling corresponding to a ground state for the subsystem that you would get from cutting off the leftmost, say, site, if I were to use the left edge state tile. So as long as you cut off the boundaries, you are guaranteed to have a configuration that generates a ground state. So it's not unreasonable to expect that the low-lying excitations here are close to ground states, because you would expect the minimal energy in this region to be the ground state energy. All right, so let me just briefly summarize then what the lower bound strategy is for the spectral gap. We first produce a lower bound on the spectral gap for the Hamiltonian restricted to the, with open boundary conditions, restricted to its tiling space, to its BVMD tiling space. And the method we use here is to apply what's called the martingale method. It was first introduced and developed by Warzel in 1996. But the particular form that I'm applying is one that I worked on with Bruno and Bob Sims. And the main calculation here is to prove a norm bound estimate of this form. Now, what is this norm here? So these G's are the orthogonal projection onto the ground state space restricted to a particular region. So if the whole region, the Hamiltonian, the spectral gap we're trying to approximate is on an interval of length L, what this operator says is that I'm trying to search for an excitation and say that I have a ground state up until the first L-3 sites, but that when I look at the Hamiltonian, or the wave function on the full interval of length L, I actually have an excitation. That means somewhere towards the end of the region, I have introduced an excitation. Now that excitation it doesn't have to be localized to that interval of length 3, it can kind of move back a little bit. But what this here tells me is that where do I think the excitation is localized to? I think it's localized to the last 9 sites. Because if this norm bound estimate is sufficiently small, what it says is that this wave function that I'm looking at that is a ground state on the first L-3 sites, but overall an excited state is almost orthogonal to the ground state projection on the last 9 sites. And it's that sort of computation that you need to apply the martingale method. Now, once we do this, we'll get a robust order 1 lower bound on the gap for the Hamiltonian restricted to the tiling space. And then I will use that in conjunction with the variation of Kanabe's finite size criterion with the isospectral relation to approximate the spectral gap for the Hamiltonian with periodic boundary conditions in its tiling space. So that's how I'll get the order 1 lower bound in the tiling space in the
Amanda,
yes.
excuse me, I think I'm confused. So I first understood that this tiling space is for description of ground state subspace. Now you're talking about proving gap within this tiling.
Yes.
So that's confusing to me.
So remember that the idea of this, we're trying to prove a order 1 gap on the Hamiltonian with periodic boundary conditions above its ground state energy.
Yes.
Now the ground state energy here is 0. So we're really trying to approximate the lowest non-zero eigenvalue of the Hamiltonian. Now the edge states, though, have been segregated out of the tiling of this BVMD tiling space. So really, what am I trying to approximate here? I'm trying to get the minimum between the second lowest eigenvalue in this subspace and the lowest eigenvalue in its orthogonal complement when I restrict the Hamiltonian to these 2 subspaces.
And what is this subspace C lambda periodic?
So the C lambda periodic is the subspace that you get from taking all of these tiling spaces that support ground states and taking their direct sum. So they happen to be mutually orthogonal subspaces. So you know that this subspace, it's an invariant subspace of the Hamiltonian, and it supports all of the ground states.
Right. But so does this space contain something other than ground state? That's
absolutely, yes. Yeah, no. This is not this is not just the ground state. So the C lambda R, I kind of glazed over this, I apologize. It's the linear combination, is the span of all of the tiling spaces. So it's, you know, for the example that I have here, there's 1, 2, 3, 4 configuration states. So this would span a 4-dimensional space, but it happens to contain one ground state.
Ah, okay. That one is the
Right.
ground state. Okay, okay.
Yeah. Right. So it's invariant, but it only contains one ground state.
Okay, okay.
So there's other states as well. Yeah.
So each connected sector contains exactly one ground state.
Right. And then what I do is I take the sum over all of these different sectors, and that's what I'm calling this tiling, this BVMB space.
Okay, thank you very much. Yeah, that's very
no problem. Thank you for clarifying. Yeah. So exactly, this invariant subspace, it does contain ground states, but it also contains excited states. So we're trying to approximate the second lowest eigenvalue in this subspace and the lowest eigenvalue in its orthogonal complement. And that's exactly why we're applying the spectral gap techniques to this tiling space. So this will allow us to approximate the second lowest eigenvalue. But since these subspaces do not contain the edge states, and we have this isospectral relation, the estimate that we'll get here for the spectral gap will be robustly order 1 in the parameter lambda. So as lambda tends to 0, this gap that we will obtain in this subspace will remain open. And then for the subspace, for the orthogonal complement of the subspace, which is where we know all of the edge states live, I'm going to use electrostatic estimates that are just based off of the Cauchy-Schwarz inequality. And the main thing here is that I do not need to use a Hamiltonian with open boundary conditions to approximate the ground state energy in this sector. And since I'm not using the Hamiltonian with open boundary conditions, its edge state energy, the minimal energy of its edge states, will not actually come into my estimate in the very end. So that's kind of the 2-minute description of what this strategy is and how it works. Let me just also briefly mention again that the spectral gap estimate would give you a lower bound on the incompressibility. So the incompressibility at 0 temperature and at critical filling, so when you're at this maximal filling of the ground state, you can write the inverse of the incompressibility in the following form in terms of the second derivative of the energy. So you get a factor of lambda here, and then you have this ratio here where this lambda plus and lambda minus, it corresponds to taking a finite volume lambda and increasing it by one site and decreasing it by one site. Now, if N is the critical filling for the volume lambda, the minimal energy in the N particle sector for lambda is going to be 0, because that's where you have, for example, the Laughlin wave function. For lambda plus, it would also be 0. But for this lambda minus, where you've shrunk the volume by 1, it would be the gap. And so this would be bounded from below by something. The gap that we have, it's robustly order 1 times the size of lambda over this prefactor here. And so this is where you can see the incompressibility, because as lambda tends to infinity, then the inverse of the compressibility would also tend to infinity. And let me just say really quickly that we also have some conjectures about where the excited states live. And the idea is to create a bulk excitation that belongs to a tiling space generated by a quasi-whole, quasi-particle pair, where more or less what you do is you take this dimer tile, you cut off the 0 at the end, and then you flip where the 0 and where the truncated monomer live. And so you can place these somewhere in the bulk of your volume. You haven't changed the overall filling of the state. You just kind of changed where the ones and the zeros are located. And you could once again introduce some additional tiles and replacement rules to generate an invariant subspace of the Hamiltonian. And we we have some bounds on what the minimal energy is in these subspaces. And it depends more or less on how far away you place this truncated monomer from its last zero. And if they're next nearest neighbors, or if they're nearest these child neighboring each other, then we expect it to be the root associated with the second excited energy state. And if they're at least separated by one monomer, then it should be a ground state energy. And we were able to get upper and lower bounds up to order of lambda squared that were tight. And for small values of lambda, at least they compared quite well to our numerical results. However, we can't construct the exact excited energy states here, which is part of the problem with showing that this is the correct subspace to look at, but this is where we believe they live. And so more work would need to be done in this setting. You can also produce exact energy states of mid and high energy with low Schmidt rank by using the voids to introduce barriers or boundaries into the states. And so you can actually identify quite a few mid and high energy states exactly using the ground states we already produced. So let me just conclude with saying that in summary, we were able to produce improve the bulk gap results from the previous works we had done with Bruno. Simone and I were able to improve these results for the nu equals 1/3 model. We can also do the same thing for the nu equals 1/2 model. That's a bosonic model, so you have to worry a bit about the fact that your Hilbert space is infinite dimensional, but this is easy to get around. The bulk gap strategy, as long as you can kind of get an isospectral relation, and you can also segregate your edge states and your excited and your ground states, a similar approach should work for other models. And the incompressibility is a consequence of the uniform spectral gap, and we do think we have some ideas of where the lowest excited energy bulk states are, but we don't have very good results there yet, but we'd like to see that in the future. So thank you very much for your attention.
Thank you very much, Amanda, for this very nice talk. So I now leave the floor to the audience for comments or questions.
Jakob has a question.
Yes.
Hi, Jakob.
Yeah. Hello. So thank you very much, Amanda. It's a very beautiful talk. Well, two points. Well, first of all, isn't it correct that the case of filling factor 1/2, which would be relevant for the bosonic case, so that is mathematically a little simpler than this filling factor 1/3 that you are studying about. So as so to say, if I want to explain the principles, then it may be easier to explain it with
So perhaps I think that you know this research area much better than I do from what I know of your work. However, in terms of I am Bruno's PhD student, so my mantra is always to look at quantum spin models, and from the quantum spin perspective and the spectral gap approaches, the reason why the fermionic model is maybe a little bit nicer to look at is that you have a finite dimensional Hilbert space, and so how, for example, the martingale method works requires a finite dimensional Hilbert space. So with the bosonic model, the Hilbert space is infinite dimensional, and so you have to be a little bit careful there. It is more or less the exact same principle here, and we did do the analysis first for the bulk gap in the 1/2 model. In terms of a talk, it's a little nicer to do the fermionic model simply because there's some kind of edge annoyances with the bosonic model that I didn't have to talk about here.
I see. Okay, but maybe I can, if I am allowed, then I'd like to ask to add a remark, namely, this is all very nice and very, very, very beautiful that one can apply things that one has learned about these one-dimensional spin systems. But one shouldn't forget that in my opinion at least, the full two-dimensional situation is an order of magnitude more difficult. And,
Absolutely.
well, I mean, there is a very simple, the simple way of seeing this is if one uses this Knabe criterion and simply compare, so to say, the Hamiltonian with Hamiltonian squared, then one sees that one has to deal with commutators, because these, well, in the one-dimensional case, then two sides, or rather two particles which are not, if you have these pseudopotentials are projectors. So if you have such, say, delta 1, 2 and delta 3, 4, they commute, but not if the indices overlap. And in the one-dimensional case, you have only, so to say, order n non-vanishing commutators, whereas for the two-dimensional situation, you have n squared non-vanishing commutators. And this, so to say, is a really serious obstacle, at least for the attempts of myself and Nicolas when we were looking at this. So my question is, so to say, have you any any ideas? You don't have to tell me any secret. You may have it up in the sleeve.
Sure.
So to say, are there any ideas how to go from this essentially one-dimensional model to two dimensions?
So yeah, let me go back to where I had the full one-dimensional model. So okay, here. Yeah, so you're absolutely right that there is it's much more complicated when you look at the full Haldane pseudopotential. And in particular, even with the full pseudopotential in the one-dimensional lattice setting, which here should correspond to the full two-dimensional system because it's just the second quantized form. It's already difficult because you don't get any zero commutators. Right, these wave functions don't actually commute, and we've been trying to overcome this now for a while, and it hasn't produced anything good. But we have some ideas, but I don't want to say too much.
Okay.
It is rather challenging, and in particular, one thing I can say is that an initial idea we had was to use a stability type argument where the fact that we know that the gap holds for this truncated version and try to treat the rest like a perturbation and apply some sort of local topological quantum order condition a la Mikolakis and Zolak. However, the problem here is the large degeneracy of the ground state space. Even if you restrict to a, say, maximally filling sector, there's so many ground states that this criterion doesn't really play well, and you can't really prove an LTQO type result. So it is much more challenging. I agree with you.
Okay, thank you. So there are all the questions, I guess, by all the people.
So thank you. I see a hand raised by Alessandro Giuliani. Please, Alessandro.
Oh, hi. Thanks for the very nice talk. So actually, my main question was essentially the same as Jakob. So I wanted to understand better connection to a full two-dimensional model. But in addition to that, can you please comment a bit more on this limit lambda to 0? I sort of saw in one of the slides in which you commented about this physical regime and Thouless regime, this limit r to 0, which in fact I couldn't match with the more natural limit r to infinity. Sure.
Okay. So first, let me just say, because these are kind of spread over two different slides, so I apologize for that. So in both, so I was interested in working in the second quantized version of the P=1 Haldane pseudopotential. So the Fock space that I'm interested in is the fermionic Fock space generated by this lowest Landau level, which here is particularly catered to the cylindrical geometry. So this one-dimensional lattice model it really just comes from doing the second quantized formalism to the Haldane pseudopotential. So here I mean, Jakob could maybe correct me if I'm misspeaking, but this is the full two-dimensional system here for the cylinder in the cylinder geometry. So all we've done is rewritten this.
Sorry, so ideally you would like to take R to infinity in this setting, or?
That would give you more of the plane geometry. That is true. And ideally we would like to be able to do this. However, part of the reason why we chose the cylindrical geometry is that when you actually look at the pseudopotential in this geometry, you get this parameter, you get this coefficient here in terms of the parameter alpha. And the parameter alpha is the ratio of the magnetic length to the radius of the cylinder. So this gives you something to play around with to make these coefficients more or less as small as you want. So naively, what we kind of felt is that in the regime of small r, which would correspond to this coefficient being much smaller, you could more or less treat the longer range interaction terms as a perturbation. So that was the motivation behind looking at the truncated model and behind looking in the cylinder geometry. So we're thinking about this parameter alpha being rather small, or excuse me, being rather large. Right. Now, if I go back to the lattice model that I'm considering, in terms of the physical regime, the parameter kappa is going to be something robustly order 1, and the parameter lambda is also going to be small when alpha is large. So this is where this limit of lambda going to 0 kind of came into our notice. I am not completely convinced that the edge states that we found in this system are the true edge states you would see in a fractional quantum Hall system. I don't think they are the true edge states you would see, because one thing we did here is we kind of factored out a scaling of the Hamiltonian. So I'm kind of skeptical that these edge states are the physical edge states you would expect in a fractional quantum Hall system. But nonetheless, the fact that we have these low-lying edge states that are preventing us from getting a robust order 1 or an accurate, I should say, lower bound estimate on the spectral gap, I think is an interesting question, because edge states do exist and they do prevent people from getting good estimates on spectral gaps. And so I think as a toy model, it was kind of a nice example to see how we can get this bulk gap. So in this limit of lambda going to 0, it's really this tau thalamus limit where you're taking the radius to 0. So that would be the thin cylinder limit.
Okay. But in this regime, alpha large, do you expect to be able to control in perspective this truncation in K? So you truncated order 3.
Yeah, so I see. So are you talking about like higher values of the truncation? Is that what you're asking about? Yeah. So one thing that
these different regimes somehow. But so
right.
I mean, you keep your R small alpha large, and then you ask yourself if in fact the higher order K correction
truncations. Yeah. So something funny that we did look into this a little bit, and something funny that we found is that if we were to truncate K to K being at most 2, so if we even just took one more term in the Hamiltonian, you would still get a frustration-free model, but your filling would be different, and it would be lower filling. And so we weren't quite sure how to kind of rectify this. One thing that we can see is that even though the higher range truncations are again frustration-free, the difference that you get of the interactions from the lower truncation and the higher truncation is a non-positive operator. So we think that part of the problem here is choosing the right values for the truncation, and it's not clear to us if higher range truncations would give you the right filling. It might be more in the limit that you would get the correct filling back for the ground state space.
Thank you.
No problem.
Okay, thank you. Other questions? So it does not seem to be the case. So let's thank again Amanda for the very nice talk and for the discussion. Thank you very much.
Thank you.